Hi, today we're continuing with the GPS disciplined oscillator, and we've got the PCBs from PCBWay. These actually came in super quick. I was waiting on components that got stuck in China, so I don't know what happened with those, but it took forever for those to arrive. These actually turned up really quick, but now they're here, we can start assembling these PCBs. But everything looks really nice. We've got really nice purple colour to it. There's only one issue that I've spotted with this PCB that we're going to have to correct. And at the top of the PCB here, you can see what's happened. For some reason, we've just got these tiny slits on these two SOT23 parts. Now, I don't really know what's happened because I had a look at the Gerber files, and these are expanded properly as you'd expect. So I don't know what has gone on. Something has been interpreted incorrectly, but we'll be able to scrape those away slightly with a knife or something and re-expose the pad for those two parts. We did also get a stencil so that we can reflow the PCB with the solder paste already on the pads, so that's what we're going to do now. I missed the shot there with the camera, but the solder paste has gone on perfectly, as you can see, so now it's time to start placing parts. Right, so that's the assembly complete for all of the surface mount parts. Today we're going to reflow the board on one of these hot plates instead of the preheating station. So this is the YOYU 946C, and I know that quite a few people have had good results with reflowing their boards on a hot plate like this. So we're going to give this a go today. I have actually got a new reflow oven that arrived the other day. I've got to have a look at that, so we'll be testing that and seeing if it needs any modifications, but for today we're going to try out this hot plate. And that's the reflow complete, so I'm just cooling this down now with the fan. And here's the finished PCB. I've not put the DAC in yet because I just want to check the voltages before I put that in. That's quite an expensive part, so I don't want to blow it up. But actually, the reflow process worked really well with that hot plate. The one thing to note with that is you probably saw there were a few tiny solder balls around some of the components. I've cleaned that all up now. But what that means is the temperature ramped up too quickly, and therefore the flux didn't operate properly and the solder balls got left elsewhere rather than being dragged into the pad. So if I'm to use that hot plate again, I probably should set it up to a lower temperature first and then ramp it up to the full temperature to reflow those parts. But the hot plate worked really well, a lot better than that preheater and the hot air, because obviously the hot air didn't blow any components around, so that worked a lot better. The through-hole parts are all in, including a couple of the parts on the back side that's just feeding the power pin into the oven oscillator. But if we have a closer look at the PCB, you can see here the reflow process worked really well on this SSOP package. So absolutely perfect reflow. I think we're about ready to test this out. So what I'll do is I'll hook it up and also put a ammeter in line so we can see the current dropping as the oven oscillator heats up. So the current's being read by the Fluke 289. Let's turn it on and see what happens. And so we're starting off at about 400 milliamps or so. We can see that starting to drop. So on the input to the 5-volt regulator, we should have our 12 volts. We've got a little bit of voltage drop through the multimeter, but it's basically there. 5 volts on the output. And 3.28 volts for the 3.3 volt rail. So the voltages are okay. We can probably put that DAC in place now, and the next thing to do would be to hook up the GPS antenna to the connection here. I'll just do it up lightly, not too spec because I haven't got a little torque spanner. And we should also be able to plug in the USB port as well. And Windows made a noise, so it's definitely picked that up, and it has enumerated. And we've now got the 1 pulse per second LED flashing, which is a good sign. That means it's picking up the GPSs. Let's have a look in the u-blox UCenter and just see whether we can communicate actually with the u-blox device. And yeah, we're able to communicate with it in UCenter. We're picking up a whole bunch of satellites, and you can see where they all are in the world. And we're able to configure everything in the configuration window. So that looks to be pretty good. The next thing we want to do is check what's going on with the oscillator, see if we can adjust it and make sure that we're getting all of the valid outputs. Right, so we've got our DAC plugged into the PCB now, and we should be able to see what the reference output from that is. It should be 2.048, and it is that exactly on the Fluke 28, and the output should be reading 0 at the moment because it's unconfigured. And yeah, we're getting 0 volts. So that's as it should be. What we should be seeing here on the output is roughly 10 megahertz. It will be being dragged down because we're driving this at 0 volts rather than at mid-rail. So let's get the frequency up on the oscilloscope. So first of all, in red is the output from a GPSDO that I've had running on my bench for many months now. So that's very stable. And in blue, whizzing past, you can see the output from the ovenized oscillator. And the reason that that's whizzing past is because it's not exactly 10 megahertz, primarily because we've set the adjustment pin to 0, so we're reading below 10 megahertz. That's its minimum frequency, but obviously we haven't tuned it to match the 10 megahertz from the GPSDO. Now, interestingly, the amplitude is not quite what I was expecting. I'm getting 0 to 2 volts. So possibly my resistor values on the op-amp circuit are not what I was expecting. So let's have a look at the output from our amplifier circuit. And so yeah, here's the output from the amplifier, and we're definitely not getting the correct amplitude. We should be getting about 3.3 volts peak to peak. So we need to have a look at that. So here's our circuit. We're getting about 1.9 volts peak to peak into this node here. And what we're doing is we are terminating that with a 50 ohm resistor, 51 ohms, it's close enough. Then AC coupling this into an inverting amplifier. Now the reason that we are AC coupling this in is because we're actually biasing this node at half rail. So this is powered by a 3.3 volt rail, and we're splitting the rail with these two resistors here and filtering it with a couple of capacitors and feeding it into the non-inverting input of the op-amp. And by virtue of the way that the op-amp works, this node also should float at that half rail point. So we need to AC couple the 10 megahertz signal into there. And then we've got a dividing network here around our inverting amplifier, which gives us our gain. So what we actually need with our 1.9 volt peak to peak to give us about 3 volts is 1.57 in gain, which means that this can stay at 2.4K, and we want about 1.5K on the input here. Now the decrease in gain that we've got with the currently fitted components doesn't account for the decrease in amplitude that we've seen. So I think we've actually got another problem, and this is the op-amp that I selected, and I did actually use this on the Symmetricom GPSDO that I modified many years ago now. However, I think I've spotted the problem already. We're feeding this from the 3.3 volt rail, and this high-speed amplifier is not designed for rail-to-rail input or output. So if we have a look at some of the specifications here, firstly you can see from a plus or minus 15 volt rail, we're only going to get 12.7 on each side. So that's certainly not going to give us what we need when we're running it from 3.3 volts. But also, this part isn't really designed to run from 3.3 volts either. You can see here, minimum 5.5 up to 36. So we're not getting the performance that we're expecting. Unfortunately, with the circuit as it is, it's going to be a little bit tricky to give us a negative rail so that we can get this close to 0 volts. So I think we're going to have to find another part. Unfortunately, we actually need a part with a very high gain bandwidth in order for this to work properly. So we're already at 10 megahertz, and effectively we're going to need something well in excess of 50 or 60 megahertz gain bandwidth on this part, possibly even higher. And so I'm going to have to really search through my parts and see if I can find a suitable op-amp to drop in here. Right, so a lot of hacking and messing around later. I've spent almost 5 hours since that last point getting this thing working, but I had real trouble with some of these op amps. So despite some of them having game bandwidth products in excess of 50 or 60 megahertz, I still couldn't get it to give the appropriate output on the 10 megahertz. So I was seeing quite a lot of attenuation of the signal, and we're also seeing some violation on the 2 input pins, basically because the output couldn't swing fast enough. We were seeing quite a lot of voltage wobbling about on one of the inputs. I finally managed to solve it. As a last resort, I swapped to some of the dual op-amp packages that I've got. This is a 180 megahertz bandwidth op-amp, and that one seems to be doing the job. Let's have a look at the output. So there's our sine wave output. This is what would typically be fed into our various pieces of equipment. And then if you had your 50 ohm termination on the end of that as well, that would bring it in line with what the signal is supposed to be. Similarly, we've got our output to our FPGA and to our microcontroller. And here we can see we've got our square wave. So we've got 2 buffers, one feeding the FPGA and one going straight into the microcontroller. We've got a little bit of ringing on the waveform. That's because, again, we haven't got the 50 ohm termination, but we've got our 0 to 3.3 volt signal, which we'll be using to process the data. So we're finally ready to check we've got control of the oscillator and also see how aged this oscillator actually is. It's currently set to basically 0 volts, which is the minimum adjustment voltage. The maximum is 8 and the nominal is 4 volts. You can see we're reading about 10 Hz under 10 megahertz. Let's try setting it to the maximum. And you can see that increasing. And now we're reading 10.4 Hz over 10 megahertz. So the oscillator looks to be in fairly good shape. Let's set it to the midpoint. So we're pretty much there on the 10 megahertz, just slightly under. But that's a very good sign that this particular oscillator has not reached anywhere near its end limits. I have had some of these 10 megahertz oscillators that have been almost out of spec. They've probably only had sort of the last hertz of adjustment at the top end. But this one looks to be in really good shape. So basically what our firmware or the code on the FPGA is going to be doing is to try and tweak the oscillator value up as close as it can get to 10 megahertz. And you can see we've got quite a lot of granularity here. We can adjust right down to the last digit and just slowly creep it up and down until we get to that 10 megahertz. So I've got some firmware to write for the microcontroller, also some VHDL for the FPGA, and there's going to be a split of tasks between the 2 devices. Primarily, the FPGA is going to be involved with all the timing critical work, so dividing down, perhaps the PLL loop and that kind of thing, and then the microcontroller can do more of the housekeeping and the stuff that doesn't lend itself to VHDL very well. Because there's a little bit more to it than just tracking the 1 pulse per second and counting the 10 megahertz output. There's some jitter on the 1 pulse per second, and that sort of follows a sawtooth type waveform. And then there's also the general drift of the ovenized oscillator, and we don't want to be tweaking the control loop all of the time so that we end up with some jitter on our 10 megahertz over time as well. So we need to sort of survey and learn how the oscillator drifts. This is all going to be done in firmware, and we also need to learn what the 1 pulse per second behaves like, and then we can correlate that all together in a nice control loop and give us very, very stable 10 megahertz output. And we probably end up storing all of that to non-volatile memory so that in the event of a power loss we can get there quite quickly. So I think it's going to be quite an interesting project. There'll be some rapid updates early on because this is going to be a full product. We're going to have the display on the front, we're going to have a distribution amplifier at the back so that we can feed it out to multiple pieces of equipment, and then eventually we need to get to a point where we've got one main board with all of this on there. So if you've got any thoughts or comments, or if you've had experience with designing your own GPS disciplined oscillator, then don't forget to leave anything in the comments down below because it's really useful for me to read through that. Don't forget to give it a thumbs up. Stay tuned for further updates, and until next time, thanks for watching.